All righty, this is the last section of Module 7, and it covers the last two series tests, that is the ratio and the root test. So in this section, we're going to use the ratio test to determine absolute convergence of a series. We'll use the root test to describe absolute convergence of a series and determine a strategy for testing the convergence of a given series. Okay. So by now, I'm hoping that you guys are getting really good at this. We know we have 12 tests, geometric series tests, telescoping series tests, the nth term test of divergence, the integral test, the p-series test, the direct comparison test, the limit comparison test, the alternating series test, the test for absolute convergence, the test for conditional convergence, and now the ratio test and the root test. Okay, so we are going to start with the ratio test. All right, so the ratio test is a test that is absolutely wonderful for factorials. Okay, we can use it for many other things than factorials, but believe it, it is wonderful. Anytime you see a factorial, you want to go in and look at the ratio test. Okay, so how does the ratio test actually work? Okay, so I try to give you little hints to remember stuff. Think ratio, root, row, ratio, root, and row. Okay, so the ratio test, you're going to compute row. And for the ratio test, it is the ratio of an plus 1 over an. And I look at that in absolute value. And I look at the limit as n approaches infinity of that expression. If the row I get is less than 1, then the series converges absolutely. If the row I get is greater than 1, then the series diverges. And if row is equal to 1, the test is inconclusive. If you can, try another test. So the ratio test is very similar, and it actually comes from the geometric series test. And the only difference between this and the geometric series test is what? What is the difference between this test's conclusion and the geometric series test in terms of rho and r? Can anybody see what's different? When does the geometric series converge?
Absolute of r is less than 1.
Okay, so the difference here is when r, for the geometric series test, we know for a fact that if r is equal to 1, it diverges. But here, if rho is equal to 1, okay, it actually will, we don't know. Okay, because for some things it could converge and some things it could diverge. Okay, so let's see. My first example is this guy here. All right, so number 1 is the sum I don't want to integral. Back up. I don't know how I got an integral. I want a sum. All right, the sum n equals 1 to infinity. And this is 1 over and then that is pi cubed to the n. Okay, so this is the test we want to do. All right, and we want to use the ratio test. So what I need you to do is to identify for me what is AN.
Would AN be what? Oh, sorry, pi cubed to the nth power.
Okay, so AN is the whole thing, pi cubed to the n. And what will be AN plus 1, the next term? What would AN plus 1 be? So AN plus 1 says in the place of n, we're going to put n plus 1. So this is going to be pi cubed. In the place of n, I'm going to put n plus 1. Okay, any questions? Okay, so it tells me to compute rho, which is the limit as n approaches infinity of the absolute value of AN plus 1 over AN. Okay, so let's look at that. So rho is the limit as n approaches infinity of the absolute value of AN plus 1 divided by AN. And that is the limit as n approaches infinity of the absolute value AN divided by AN plus 1. I have one fraction divided by another fraction. So when I take, so I'm going to take AN plus 1 and divide by AN. That's going to give me pi cubed to the n divided by pi cubed to the n plus 1. Okay. So that says rho is the limit as n approaches infinity. And so now I can see the pi cubed to the n's are going to cancel, and that's just going to leave me 1 over pi cubed. And that limit as n approaches infinity is 1 over pi cubed. That number is less than 1. All righty, nice and simple, all done. Rho is less than 1, so the series converges absolutely. So we can conclude the summation n equals 1 to infinity of 1 over pi cubed to the n converges absolutely. Okay, any questions about that?
Yes. My question is, how do you get from pi cubed to n? Well, I'm sorry, from that absolute value to 1 over pi cubed again.
Okay, all righty, I'm going to do that. How about I do that on the side? Okay. All right, so I have pi cubed. First off, the terms are positive, right? Pi is positive, 3 is positive, pi cubed is positive, and then you raise it to the n, and n is greater than or equal to 1, so that's all positive. So I can drop the absolute values because everything is positive. But then I have pi cubed to the n divided by pi cubed to the n plus 1. So that's pi cubed to the n divided by pi cubed. Yeesh, what in the world happened there? Okay, divided by pi cubed to the n times pi cubed. Because it's raised to the n plus 1 power. So therefore, these are going to divide out. And that just leaves me 1 over pi cubed.
Thank you.
You're welcome. Okay, any questions about that? Okay. Okay, here's my next example. Number 2. Sum n equals 1. Uh-oh, back up. To infinity of 4 to the n over n factorial. Okay, so as I said, the factorial problems are best suited always for the ratio test. Okay, all right, so we identify an. So an is 4 to the n divided by n factorial. And an plus 1, somebody want to tell me what an plus 1 is, please?
Would it be 4n plus 1 over n factorial?
What about that n in the denominator?
Oh, n factorial plus 1?
Almost. N plus 1 factorial. So the
Okay.
n changes to n plus 1, that stays, and then we get the factorial. Okay, is that clear?
Yeah.
Okay, all right, good. All right, so now we have to compute rho. So rho is the limit as n approaches infinity of the absolute value of an plus 1 divided by an. Okay, so that's the limit as n approaches infinity. So now, first off, everything's positive, so I'm going to drop the absolute value. You'll see that the absolute value comes into play when we have something like -1 to the n or something like that. Okay, so an plus 1 gets divided by an. So I can put an plus 1 as 4 to the n plus 1 divided by n plus 1 factorial. And I divide by an, which means I multiply by its reciprocal. So that means I get n factorial over 4 to the n. Okay, so this part, this is an plus 1. And this part is 1 over an. So I get exactly what I need. Okay, so one of the things I would tell you to do in these problems is always put like terms together. It is much easier to understand the problem. I'm going to do the limit as n approaches infinity. Well, I have 4 to the n plus 1. And that looks like 4 to the n. So I'm going to put that over top of 4 to the n. And then I have n factorial. And I'm going to nicely put that over n plus 1 factorial. Now, if you remember just from the problem before, the 4 to the n is going to divide with the 4 to the n and only leave one of them left. So this is the limit as n approaches infinity. So I'm going to get 4 to the 1 left in the numerator, because 4 to the n and 4 to the n divide out. And if you remember from the factorials the other day, I will make a new comment so we can just remember. We said n+1 factorial just basically said you take n factorial and you add on one more term. So therefore, when I divide this n factorial, so this becomes still n factorial over, this is n+1 times n factorial. And as you can see, the n factorials are going to divide out. So I get rho is equal to the limit as n approaches infinity of 4 divided by n+1. And what is that limit? As n goes to infinity, what is that limit?
Four over infinity.
Yes. Okay, we still having some issues with being able to evaluate this limit. Anytime you have a number in the numerator and the bottom goes to infinity, the whole thing goes to 0. So this limit is 0, which is less than 1. So we can conclude that the sum n equals 1 to infinity of 4 to the n over n factorial converges. Absolutely. Okay. Any questions about that?
I have a question.
Yes, Peyton.
So I'm back at when you're crossing out like terms in the 4n+1 and then divide by 4n. What's only left is +1, but how do you still have 4?
Because 4 to the 1 is 4.
Oh, duh. Okay, and then the next part is the n+1.
So n plus 1 factorial is n plus 1 times n factorial.
Okay.
So therefore, you can divide out the n factorials and only leave the n plus 1. Peyton?
Yeah, I got it.
Okay. All right. Oh, here's number 3. Okay, so number 3 is the sum n equals 1 to infinity of e to the negative n times n cubed. Okay, so we need to determine this series. All right. So, I guess if I really wanted to do it very hard, a difficult problem, I could do this problem by parts. It's not going to be fun, but I could use the integral test and do it by parts. That would work. Okay. I clearly see that the F term goes to 0, so I'm not going to be able to use that test. So let's look and see using the ratio test. So AN is e to the negative n divided by n cubed. Anybody want to give me AN plus 1? AN plus 1.
an plus 1 will be e to negative n plus 1 over n plus 1 cubed.
That's right. Okay, so now we have that. So now rho is the limit as n approaches infinity of the absolute value of AN plus 1 divided by AN. I'm going to drop the absolute values because everything is positive. AN plus 1 gives me e to the negative n plus 1 divided by n plus 1 cubed. And then I have to multiply by the reciprocal, so I'm going to get n cubed over e to the negative n. Okay, again, I like terms over like terms. So this says rho, it's the limit as n approaches infinity. I'm going to get e to the negative n plus 1 divided by e to the negative n. And then I'm going to get n cubed divided by n plus 1 cubed. Okay, so if I simplify this, I get the limit as n approaches infinity. I can see e to the negative n and e to the negative n clearly are going to divide out, which gives me e to the negative 1 or 1 over e. And then over here, I still get n cubed over n plus 1 cubed. And so now really what I need to find is the limit. The limit as n approaches infinity of n cubed over n plus 1 cubed. So if I can find that limit, then I'll be able to have, my answer will be 1 over e times the other limit. Okay. Well, this gives me 0 over 0. I'm sorry, infinity over infinity. So on this, whose rule can I use?
Hospital's rule.
L'Hopital's rule. And that says that the limit as n approaches infinity of 3n squared times 3 times n plus 1 squared. And that again is infinity over infinity. So L'Hopital's rule again. So that's the limit as n approaches infinity of 6n squared over 6n plus 1.
Shouldn't it be 6n since it's 3n squared?
Wait a minute. This should be 3n squared.
And the other one should be 6n.
Yeah, thank you. I looked at it wrong. This should be 3n squared. And this should just be 6n. That's, come on now. Just be 6n over 6n plus 1. And one more time. So that's the limit as n approaches infinity of 6/6. And that's 1. Okay, so now we finally get rho. The limit as n approaches infinity of 1/e times the limit as n approaches infinity of n cubed over n plus 1 cubed. So that is 1/e times 1, which is 1/e, which is less than 1. So we can conclude, I got to remember what it looked like. We can conclude sum n equals 1 to infinity of e to the negative n times n cubed converges absolutely. Now, I can't believe I have only examples of convergent series. That doesn't make sense. I don't have one that diverges. Oh, there we go. Oh, it didn't capture the whole thing. Let's go back and try it again. 2n factorial over n factorial n factorial. All right, I'll get it this time. Okay, there we go. Number 4. Okay. So we have the sum n equals 1 to infinity fraction on the top 2n factorial. Bottom, I have n factorial, n factorial. Aha. Okay. This one uses a lot of factorials here. All right. An is 2n factorial divided by n factorial, n factorial. An plus 1. Now that's a tricky one. What's an plus 1?
Would it be open parentheses 2 n plus 1 close parentheses factorial?
Okay, I need another parentheses there. You see that?
Yes.
Okay, 2 has to multiply n plus 1. Okay, keep going, Caesar.
And for the other one, I got the, well, parentheses n plus 1 close parentheses factorial, and then and the open parentheses n plus 1 factorial there.
Gotcha. That's right. Okay. So the n factorial, the whole thing, you can't just write 2n plus 1. You have to write 2 times n plus 1. Okay, so let's compute rho. So rho is the limit as n approaches infinity of the absolute value of an plus 1 over an. So that's the limit as n approaches infinity. Okay, everything's positive. I don't need the absolute values, but I do know that it's an plus 1 over an. So an is going to be the 2 times n plus 1, that whole thing factorial divided by n plus 1 factorial times n plus 1 factorial. And then when I divide by an, I multiply by the reciprocal. So I'm going to get n factorial divided by 2n factorial. Okay, so again, we're going to put like terms on top of each other. All right, so I get rho is the limit as n approaches infinity. So now I'm going to get, so I'm going to write this out. So that looks to me like 2n plus 2 factorial divided by 2n factorial. And then this looks like n factorial divided by n plus 1 factorial times n plus 1 factorial. Okay, any questions to that stage?
Okay.
Victor?
Oh, sorry. I was wondering what was the purpose for the two n factorials?
I'm
that's
sorry,
happened.
say that again.
I was wondering what was the purpose of the two n factorials towards on the right side, or when you're multiplying?
Okay, so this first piece, all right, that's a good question. Okay, so this first piece right here is an plus 1. And this is 1 over an. Remember, it has to be an plus 1 over an, right? So that means when I'm going to take this fraction right here and divide by this fraction. That's an plus 1 divided by an. But when I divide by a fraction, I multiply by its reciprocal. So an, which is here, gets flipped upside down because that's its reciprocal. So that's why I get n plus n factorial over 2n factorial.
Okay, thank you.
All righty. Okay, now here's where it gets tricky. So we already know that n plus 1 factorial says it is n plus 1 times n factorial. So we already know that. Okay, so that's going to give us that n factorial over n plus 1 factorial is simply 1 over n plus 1. Okay, so we're going to get that. Now, what happens with 2n plus 2 factorial? Well, we get 2n plus, that doesn't look like a 2. Let's do that again. 2n plus 2 factorial says, well, we get 2n plus 2. Then we're going to get 2n plus 1, that's 1 less. And then we're going to get 2n, and then we're going to get 2n minus 1. And we're going to go all the way down to 3 times 2 times 1. But this whole piece is simply 2n factorial. So that tells us that 2n plus 1 factorial, I'm sorry, 2n plus 2 factorial is simply 2n plus 2 times 2n plus 1 times 2n factorial. Okay, so now let's see what rho is. All right, so rho is the limit as n approaches infinity. So I get 2n plus 2. Well, that's going to give me 2n plus 2 factorial is 2n plus 2 times 2n plus 1. All right, times 2n factorial. And that is over 2n factorial. And then I'm going to get n factorial and n factorial. And this is over n plus 1 times n factorial times n plus 1. Excuse me. N factorial. Whew,
Bless you.
Bless you.
thank you. Oh my goodness.
Bless you.
Thank you. I need it. Okay, so all that divides out. It's getting warm. Hey, fever. Rho is equal to the limit as n approaches infinity. So now I get 2n plus 2 times 2n plus 1 divided by n plus 1 times n plus 1. And I want you to prove to yourselves that that limit is 4, which is greater than 1. So we can conclude that the sum n equals 1 to infinity of 2n factorial over n factorial times n factorial diverges. Okay, there are going to be some that you will get, the limit is 1. All you can say is the test is inconclusive. Okay. Last test, guys. This is the root test. We made it, 12 tests. Okay, so here's the root test. And it says you never use the root test for factorials. We do not know the square root of a factorial. Okay, so for the root test, we want to again have summation an as a series. We're going to compute rho, which is the limit as n approaches infinity. This time we're going to be taking that is not right. This should be the nth root of an. Okay, the nth root of an. Then if rho is less than 1, then the series converges absolutely. If rho is greater than 1, the series diverges. And if rho is equal to 1, the test is inconclusive. Okay, so this is the root test. All right, so here is a nice quick, easy, 1 over 2 plus 1, 2n plus 1 to the n. I don't even need to copy that. So this is the summation. Okay, stop it. N equals 1. Great. N plus 1. All right, this one screams root test. Okay, because it's got something in it that's to the power of n. So when I take the nth root of it, it goes away. Okay, so an is equal to 1 over. Is that a question? I did do attendance, Jaquan. I can go back in. Let me write you down. Okay. Okay, so therefore rho is equal to limit as n approaches infinity of the nth root, so that you gotta take the nth root of the absolute value of an. So that's the limit as n approaches infinity. So that is going to be the nth root of 1 over 2 n plus 1 to the nth power. So now we all know if you take the square root of something squared, you get that thing, provided what's inside is positive. So we're taking the nth root of something to the n. So we get rho then is simply equal to 1 over the limit as n approaches infinity of just 1 over 2n plus 1. And as n goes to infinity, that limit goes to 0, so that's less than 1. So we can conclude the series converges. Summation n equals 1 to infinity of 1 over 2n, whoops, converges. Absolutely. Okay, any questions about that? Anytime you have powers to the n, you take the nth root, they go away. So anytime you have something that like that, it screams the root test. All right, so what's the next example? Oh, this is another one, another easy one. 4 to the n over 6n to the n. Why don't I give it some oomph? I'll give it some oomph. Okay, so let's do number 2. Summation n equals 1 to infinity minus 1 to the n times 4 to the n over 6n. Okay, there. Now I made it something different because all the other stuff, everything we've done so far is positive. Let's do a negative one. Okay. So an is minus 1 to the n of 4 to the n divided by 6n to the n. All right, so for this problem, it says we need to have the absolute value. Okay, so we need to compute the absolute value of an. And so now the minus 1 to the n can go away, and we get 4 to the n over 6n to the n. All right, so therefore rho is the limit as n approaches infinity of the nth root of the absolute value of an. So that's the limit as n approaches infinity of the nth root of 4 to the n divided by 6n to the n. So 4 to the n, so now you got to remember how these rules work. This now becomes the nth root of 4 to the n divided by the nth root of 6n to the n. Okay, so rho is then the limit as n approaches infinity. So when I get the nth root of 4 to the n is just going to give me 4. And then the nth root of 6 to the n is just going to give me 6n. And as that n goes to infinity, that goes to 0, which is less than 1. So we can conclude that the summation n equals 1 to infinity of minus 1 to the n, which is an alternating series, mind you, 4 to the n divided by 6n to the n converges absolutely. Okay, any questions about that? All righty, so that is the end of module 7. Module 8 will be on power series, and then we will be done. I just want to make a couple of comments. One, I posted information about the date of the final. All right, so your final is Monday, May the 2nd. It will occur at 1 o'clock in our regularly scheduled room. It will be 2 hours long. You will not have a calculator. That's first piece of information. Second piece of information is that your makeup or retake exam will occur on reading day. Okay, so you can do it anytime you wish on reading day. You need to sit down to the computer, make sure nobody is bothering you, because you need 75 full minutes, and I'm gonna give you an additional 15 minutes to take pictures and put it into one PDF file. I'll give you more information about that, and submit one document. I don't want 5 pictures. I'm not taking 5 pictures. I will take one document and one document only. Okay, so that will, you can turn that in on reading day. That all the tests will be there, but you are only allowed to open the one test that you and I have agreed upon. Third, I've been getting email as to why can't I take this test? I didn't do well in that test. I don't want to take that test again. Okay, again, you have a professor that cares. So the purpose of this course is that you will learn the material. So the test that you did the worst in is the test that you really don't know the material. So by being able to study and learn the material, you will be able to take a retest on that topic. Okay, you don't get to take a retest on something that you halfway did okay on. You need to learn the material that you didn't learn. Okay, so that's why your retake, if you're taking a test over, can only be on the test that you did the poorest on. Okay, are there any questions about this? Any questions? Okay, please have a wonderful and safe holiday. I will see all of you on Tuesday.
Have a good one.
All right, you too.
Dr. Light,
Yes.